Okay, this is the second attempt at this video because there was a massive typo in one of the problems that I was using and it completely train wrecked what I was trying to do. And rather than try to recover from it, I thought, let's just start over again. So I lost about 15 minutes of my life trying to do that. This video is going to talk about special types of systems, and the video and demonstration and the assignment itself are probably going to be pretty short. So I thought this might be a good place to put a word about word problems. So one of the things that's missing in this Algebra 1 video series when we get to the systems is the section on systems word problems, and there's a reason for that. And I wanted to give you an example of what a systems word problem might be like. And I did make up these numbers on the fly, so forgive me if they're terrible. But a farm sells 2 goats and 5 sheep for $350. 4 goats and 3 sheep sell for $300. What is the price of 1 goat and 1 sheep? And the way you would go about doing this is you would say something like 2 goats times the price of the goat. So G is the price of a goat. Plus, what do we got here? 5 sheep times the price of a sheep. And together, the cost of the goats and the cost of the sheep is $350. And then we have another situation here. We have 4 goats and 3 sheep, and that total price is $300. And then we're asked what's the price of 1 goat and 1 sheep. And it's not a difficult problem to do. Most of them will have some kind of a vibe like this. You'll see stuff like the price of an adult, to find the price of an adult ticket and a child ticket if 5 adults and 3 kids go to the show for $40 and 2 adults and 7 kids. That sounds horrible, but you go in for $25. And so you have to get the price of each ticket. Sometimes there'll be a little bit more variety. I know I've done ones that are like, Sally has $5 bills and $10 bills in her wallet. They come to a total of $70, and there are 15 bills. How many of each kind of bill does she have? I made that up on the spot, so don't try to do it. The problem that I have with systems word problems as they appear in an algebra curriculum is that they're stupid. And the reason I think that is because this situation will never happen. The farm will tell you the price of 1 sheep and 1 goat. They'll tell you on the phone, or they'll post it on their website or on a sign. You never go to a dinner or a show or a concert or an amusement park where they don't publish the price of the tickets. There is never a situation where you would figure out the price of the goats and the sheep by writing and solving a system of equations. That being said, they do make for good intellectual practice. They're good for figuring out how to read a problem and translate it into an algebraic equation, especially when there's a little bit more variety in them. But as far as practical use goes, they're generally pretty dumb. So I don't like to teach them. That is not to say that there aren't great systems word problems out there. They're just not usually in an algebra book. The best systems word problem that I remember, and it wasn't a systems word problem, which is probably why it was good. It was actually a physics problem in a physics class. It was in an applied mechanics class that I took in college. And it had something to do with a beach, and that's the water. And a volleyball net was on the beach, and there were guide wires attached to the volleyball net, not going into the water, but you get the idea. And we had to calculate the tensile strength needed for the guide wires, and we needed to know like the angle of the incline of the beach, and then be able to figure out like the force of gravity, and then what component was parallel and perpendicular to the surface, and then all of the guide wires were pulling on the pole, and like we had to put it all together with all these forces that would be acting on it, and we had to figure something out. I don't remember what it was, but it was a great problem, and it was a problem that involved construction and things like that. And so I do want to encourage you that as you're learning about systems of equations, there are applications to it, and you'll typically see those in a science class or an engineering class, but you probably won't see them in your math class, and you'll think, why can't I just ask the person at the ticket counter the price of a ticket? Well, you can, which is why this is a silly problem. That being said, again, like I just said, you do whatever problems your teacher assigns. If you've got to practice the problems, just consider them good exercise, like running around a track is good exercise. You don't go anywhere when you run around a track, but it is still like, it's good for your body and it's good for your fitness, and it's just a good thing to do, even if you are running around in circles on a track. So that's how I feel about systems word problems, and why I don't particularly like to teach them, or I'll touch on them so that students can get a taste for what it's like to go from the verbal description into the mathematical equation, but I don't typically like to spend a lot of time on it. So that being said, let's talk about our two special systems and hope that I don't train wreck into a typo. The first special system is 2x plus y equals 3 and 4x plus 2y equals 8. And to embed review into this video, I am going to review the different ways that you can solve this. This is a plus sign. I don't know if I said, well, it won't, there we go. I don't know if I said plus or not, but it wouldn't let me, obviously wouldn't let me make a plus sign. So for this one, we're going to review the substitution strategy. I want to embed the review into the lesson so that you can review the substitution method. So for the substitution method, we're going to take that top equation and get the y value by itself. So 2x minus 2x is 0, which is going to get our y value by itself, and we'll have 3 minus 2x. And then we take that and we plug it into the other equation. So the way your substitution works is you take out the y, so the y is going to come out, and the 3 minus 2x is going to go in its place, and we can do that because they're equal to each other. And then we'll just go ahead and solve this. 2 times 3 is 6, 2 times negative 2x is a negative 4x, and then something interesting happens. You have 4x minus 4x, which is 0. And you're left with 6 equals 8. And I mentioned back at the beginning, I said when you're doing a problem like this, your first instinct is probably going to be, I did something wrong. And now you can see why. Because if this happens, yeah, you're probably going to think you did something wrong. And it's not a bad idea to check, because these are not common. If you're getting something like this for every problem, something is probably going wrong. But they are things, and they can happen. Now, this is what's called a fault statement. 6 does not equal 8. And what it means is that this system actually has no solution. Okay, and there's a couple other words that go with it. There are words that you might see in a college textbook, but we won't get into them in Algebra 1 video. That we just say no solution. Okay, this system, when you go to solve it, you end up with a false statement, which means there's no values for x or x and y that will actually work for both of them. Now, to explore that a little bit more, I do want to look at the graph. And hopefully by this time in this lesson series, if you've watched all or most of them, you've kind of realized that the graphing and the equations, they're connected, and a graph can often give you insight into a different way to look at a problem. So I'm going to take these two equations and solve them for y so that we can look at what the graphs are. I just did this one, the first one you can get the y by itself, but this time instead of saying 3 minus 2x, which is totally fine for that, I'm going to write it as negative 2x plus 3. Just because that puts it in my y equals mx plus b form, and it's going to be a little bit easier for me to graph. Over here, I need to get rid of the 4x, so we'll subtract the 4x from both sides. And just like on the left over here, I'm going to write it in the order negative 4x plus 8 instead of 8 minus 4x. And now on this one, we do have to divide everything by 2 to get y equals negative 2x plus 4. Now what you might notice about the two equations is that they do have the same slope, but they have different y-intercepts. So let's take a look at what those lines look like when we graph them and see if we can figure out some patterns there. So the first one was negative 2x plus 3. So I'm going to go up to 3, and then I'm going to count down 2 and write 1 to get my other point, and then we'll go ahead and connect those. And the other one was y equals negative 2x plus 4. So we have the y-intercept at the 4, and I'm going to count down 2 and write 1. And it's going to be hard for me to draw, but what you should notice is that these lines are parallel because they have the same slope. And what that means is there is no intersection. So these lines are going to go on forever and ever and ever, and they are not going to cross, which means there's no intersection, which means there is no solution. If you think back to the first lesson in this unit, we did solving systems by graphing. And what you've got here is a picture of all the points that make the first equation true, a picture of all the points that make the second equation true, and we realize, nope, there actually is not a point that makes both of the equations true. There's no x and y pair that are going to work for both of those equations. So that's the first kind of special system. It's the kind where there's no solution and you go to solve it and you end up with a false statement. The second type of special system is going to do something different. And this is the one that had the typos. So I'm about 12 minutes into the video. And this is about, like, I started doing the problem out and it just didn't work. And it was just so bad. So this one we're going to solve with the elimination strategy. Again, just to review the elimination strategy. And so if I wanted to, say, get rid of the y's, I would need a negative 2 in front of this y. So I'm going to go ahead and multiply the bottom equation by negative 2. And we'll leave the top equation alone. So we'll copy over the 4x plus 2y equals 6. And on the bottom, we're going to have negative 4x minus 2y equals negative 6. And immediately you can probably see that something weird is happening here. Negative 4x plus negative 4x plus negative 4x is 0. 2y minus 2y is 0. And 6 minus 6 is 0. And again, you can see why I said at the beginning of the video, these are the kind of problems that when they show up, your first instinct is probably going to be, what did I do wrong? Because you're just not expecting this to happen. This is what is called a true solution or true statement, and it means there are infinitely many solutions. Okay, and what it really means, you might hear like many solutions. That is SLONS as an abbreviation for the word solutions right there. What that means is that there are actually an infinite number of pairs of x and y that make this system true. Not just one point, but an infinite number of points that will make this true. Now, don't say all points. So I'm not even going to put that in writing because I don't want anybody to write it down. Don't say all points. It's not all points. All points are not a solution to the system because there are plenty of points that don't make either of them true. It just means that there are an infinite number that do work. So as with the last one, let's take a look at what this does graphically so we can see what we're working with here. So we have 4x plus 2y equals 6, and the other one is 2x plus y equals 3. We will subtract the 2x from both sides, and we get y equals negative 2x plus 3. On the other equation, we're going to subtract 4x from both sides. 4x minus 4x is 0, leaving us with a 2y. I'm going to put that in my slope-intercept order there, negative 4x plus 6. Divide everything by 2 to get the y by itself. And what you should notice when you start rearranging them is that they're actually the same line, just written two different ways. So that's why it's showing up as infinite solutions. Let's take a look at this. I know this is going to seem silly, but the first line has that y-intercept of 3 and then a slope of -2. So we go down 2 and right 1. And we go to graph it. And that's all the points that work for the first equation, for the red equation there. And then your second equation we'll do in blue, and that has the same y-intercept and the same slope, and essentially it's the same line. Now again, to clarify, it's not all points. That point doesn't work for either of them. Not all points, because there's a point that's not a solution. So it's definitely not all points. What you could say is all the points that work for one also work for the other. But I like to say infinitely many solutions because there are an infinite number of points on those lines or on that line. So there are an infinite number of XY pairs that are going to make the system work here, but it's definitely not all points. So just be careful about how you phrase that. Now, a couple of things that might be worth noting, and then I'll give you a few practice problems, but there's really only the 2 situations that might turn up, and they're not super, super common. It's not like you're going to be seeing these all the time. In fact, there are whole years when I don't even show my students these. These are just not that common. But if you were to see something like this, x plus y equals 8, okay, and then x plus y equals -1. Somebody who's pretty experienced with math would say right off the bat that has no solution. And what they're noticing there is you actually have the same thing on both sides of the equation here. If x plus y does equal 8, then x plus y can't be equal to -1. It doesn't matter what the combination of numbers is. If they add up to 8, they add up to 8, and they're going to add up to 8 any way that you slice or dice them. They're never going to add up to -1. So what you're looking at there is a completely impossible thing that could happen. Like that wouldn't happen. And you could go through the algebraicness of this and go ahead and try to solve it out. And so for this one, we'd have -x plus -y equals +1. X minus x is 0, y minus y is 0. And we end up with 0 equals 9, which is false or no solution. But again, an experienced person will look at that and say, well, both of these statements can't possibly be true. The other thing that you can look for that can tip you off is if one equation is a multiple of another one. And so if you take this equation here and you divide everything by 2, you're going to get the bottom equation. And teachers can do some sneaky little things to make it a little bit harder for you to see that. But those are the things that I would look for. So again, pretty short lesson. Half of this video was explaining why I think word problems with systems are silly. And we have a few practice problems. I just want you to work a couple of these out so that you get a little bit of a sense of what they feel like. So you'll know if you get something like this, whether it is what it looks like or whether you did make a mistake in another problem. So I will put a few problems up to practice on. All right, just 3 practice problems this time. First one is 3x minus 2y equals 0, 3x minus 2y equals -4. Second is 2x minus 6y equals 5, 3x minus 9y equals 2. And then the last one, 3x minus 2y equals 3, and -6x plus 4y equals -6. And what I'm going to encourage you to do before you try working them out, and you should work them out, so work through an algebraic or graphical solution regardless of what you think is going to happen because the practice is good. But see if you can look at them and predict what they're going to do before you do them out. Then unpause the video and check your answers. Whoops. Okay, there we go. So for the first one, I multiplied the bottom equation by -1. Essentially, I didn't write the 1. Hopefully you're okay with that. I just distributed negative and multiplied everything by -1. And that gave me 0 on the left and 12 on the right. So 0 equals 12 is false. There are no solutions. And if you need to pause and just kind of study that for a second and make sure it makes sense. If you need to go and solve it for y and try to graph it, and just make sure that you feel solid in that. Second one, I multiplied, my attempt was to get rid of the x's. So I multiplied the top equation by 3 and the bottom equation by 2, and then I chose to make the bottom one negative only because I had a little bit more space on my slide there to work with. And that gave me 6x minus 18y equals 15 across the top, and negative 6x plus 18y equals negative 4 across the bottom. Negative 6 and 6x and negative 6x and negative 18y and 18y, they all cancel out, giving me 0 equals 11, which of course is false. Just for the record, so you know, you can get other kinds of false statements. If you're doing elimination, the elimination method, you'll often end up with that 0. You might even always end up with the 0. If you are doing a substitution method, you can get something else that's false, like we did over here, 6 equals 8. So I don't want you to think it's always 0 equals something. It really just depends on the strategy. Last one is infinitely many solutions, and I went with trying to eliminate the y's. In this case, I think is what I was going for, although I guess it's impossible to tell, but because I ended up with 0 equals 0, and that is a true statement, which means this is two different versions of the same line, so infinitely many solutions. And you can get other true statements. I think the 0 equals 0 is more indicative that you've used the elimination strategy, but you could get anything. You could get like a 3 equals 3. Okay, or 5 equals 5, or negative 3/4 equals negative 3/4, anything that would be considered true. So hopefully that lesson covered this little glitch technicality that comes up. They do show up, these special systems do show up, but they're not very common. So if you start seeing them a lot, probably something is wrong. And when you do see these solutions come up, it's not a bad idea to just check and make sure that you didn't make a mistake, because they're not really, really common. But so we got that in, and we talked a little bit about word problems. I know that I've got this, he's over this lesson, that I'm a little bit kind of sardonic when it comes to the word problems, but you will see them. If your teacher assigns them, you do them, and that's all there is to that. It's really good exercise. Just you could ask the person behind the counter what the price was. So I will see you in the next lesson. We have one more lesson in Unit 7 to talk about systems of inequalities, and then we're going to leave lines behind. We will have covered everything we need to about linear equations, systems, and inequalities.